and welcome back to the video lecture series of the Fundamentals of Machine Design. In this lecture, we are going to see a few derivations for different kind of shapes to calculate the moment of inertia for the particular different shapes. In the previous lecture, we have seen the basic concepts of the moment of inertia, centroid and center of gravity, and the terms related to them. And we have also seen two different theorems which will be utilized in today's session so that you can understand easily if you have revised those different types of theorems in the previous lectures. Okay, so let's get started with the first derivation, and this derivation is also asked in your GTU. So pay attention over here, because this is the derivation of the moment of inertia of a rectangle. So whenever you are dividing your current shape into a basic shape of a rectangle, then you must know the formula to calculate the moment of inertia about the axis passing through the center of gravity, or passing through the base of the rectangle, or anywhere around the axis which is demanded by the example. So you need to calculate the moment of inertia about that particular axis for the shape which is rectangle. So you need to identify first the shape. So the shape is shown in a figure like this, and as you can see, the shape can have the depth d and the width b, and this shape can be divided into the two equal parts, because the centroid or the center of gravity of the rectangle is always in the middle of the part, and that's why the line which is passing through the centroid of the rectangle is this middle line. Okay, so the x-axis is representing the centroidal axis about that about the x-axis line. Now, if you consider the distance from this centroidal axis, that is nothing but the d by 2 from the top of the rectangle and d by 2 from the bottom of the rectangle. Now, our intention is to find out the moment of inertia for this particular rectangular shape around the axis passing through the centroid of the rectangle. So consider an elemental strip parallel to the axis. So as you can see in this diagram, there is a strip which is parallel to the x-axis axis, which is passing through the centroid at a distance y from it, which is having the thickness dy. So the thickness dy and having the distance y is provided to calculate the moment of inertia of that particular strip around the center of gravity. So if you want to find out the area of that strip, that area is also the rectangular area, and that's why our area of the elemental strip is represented by the dA, which is nothing but the b into dy. Now what is b? B is the width of the strip, and the width of the strip is equal to the width of the rectangle. So dy is the height of the strip, and into the b, that is the width of the strip. The multiplication of both will give you the answer of the area of the elemental strip. Now our intention is to find out the moment of inertia about the x-axis axis. So what is the basic formula to find out the moment of inertia? That is nothing but the area into distance square. But our intention is to find out the whole moment of inertia of the whole rectangle. So what we are going to do is, integration about that particular axis for the limits minus d by 2t plus d by 2. So for this particular limits, we will put the value of the dA, that is nothing but the b into dy into y square, where b is the constant, and that's why it can be taken out from the integration, and the integration of the y square is nothing but the y cube by 3. And if you put those limits, that is plus d by 2 and minus d by 2, you will have the simplified answer like this. As you can see, the answer comes out to be the bd cube by 12. So this is the formula of the moment of inertia of a particular rectangular shape about an axis which is passing through the centroid of the rectangle. Similarly, consider an elemental strip parallel to the y-y axis. Now where is the y-y axis? Y-y axis is this vertical axis, and the strip is parallel to this vertical axis having the thickness that is dx and distance from the vertical axis that is x. So these are the parameters which you will utilize to calculate the moment of inertia of this particular elemental strip. Now our intention is to find out the moment of inertia about the vertical centroidal axis. So vertical centroidal axis can be calculated using the same method that we have used to calculate the moment of inertia about the horizontal centroidal axis. So what we are going to do, we are going to apply the basic formula of moment of inertia. For that we need the elemental strip area, and that can be calculated using the same method, that is dA equals to d into dx. Now this is the area of that particular elemental strip. Now we will multiply the distance square in order to calculate the moment of inertia. So dA into x square will give you the moment of inertia of that elemental strip. But our intention is to find out the moment of inertia of the whole rectangular section, and that's why we will integrate that term with the limits minus b by 2 to plus b by 2. Why is this limit is applied? Because we have assumed that in the left portion the distance is negative, and in the right portion the distance is positive as per the basic sign convention of the Cartesian coordinate. Okay, so we have considered the extreme limits. Over here the distance is minus b by 2, over here the distance is plus b by 2. So if you apply those limit in the integration and do the integration by keeping the d as a constant, and integration of x square is nothing but the x cube by 3, then you will have to apply those limit in this integration of x cube by 3 and simplify that equation, and you will get the answer of the Iyy as a db cube by 12. So we have two formulas. As you can see, the shape is the same, that is the rectangular shape. But for the rectangular shape, if you want to find out the moment of inertia about the x-axis, then you will use the bd cube by 12, and if you want to find out the moment of inertia about the y-axis, then you will utilize this formula, that is db cube by 12. Okay, so these are the two different formulas for two different axes, and that's why you will have to remember which axis is asked in your example, and based on that axis you will utilize the formula which is given in this derivation. Okay, so we will see another derivation for different shape like this. Now if you first we will see that if the moment of inertia about the line passing through the base of the rectangular section is asked, then which formula will be utilized? The same method to calculate the formula will be used, but the formula will be like this, that is bd cube by 3. Okay, so our formula which is used to calculate the moment of inertia at the base of the rectangle is bd cube by 3. If you remember this formula, then you can easily apply that formula in your example. If you don't remember that formula, you don't have to worry about that, because you can directly apply the parallel axis theorem between these two axes, because we know the formula about this axis, and that is nothing but the bd cube by 12. And if you want to find out the moment of inertia about this axis, then you will get the answer using the parallel axis theorem, that is ig plus ah square. Okay, so if you apply this formula, then you will get the answer as bd cube by 3, and that is our intention, which is given directly over here. So if you know this answer, then that is very good. You can apply that answer directly, and you can reduce your length of the sum. But if you don't know this answer, then your basic concepts are going to help you to find out that particular formula, and you can easily calculate the example if you know the basic concepts of the parallel axis theorem. Okay, so these are the basic things which you need to remember before starting the example. Now we will see another derivation, that is the derivation of the moment of inertia of a triangle. Now this is another basic shape which we generally divide into the parts, and we have taken an example of a general triangle, so you don't have to worry about any different types of triangles. So the height of the triangle is h, the base of the triangle is b. So everything is given in this figure. Now this x axis is passing from the centroid of the triangle. This DE axis is passing from the top of the triangle, and this BC line is passing from the base of the triangle. You can be asked any moment of inertia passing through any axis. Okay, so about any axis which can be passed through the top, center of gravity, or the base of the triangle. So first we will see the moment of inertia about the base, BC of the triangle. So as I said, you can be asked a moment of inertia about any axis, whether it is passing from the center of gravity or the top or the bottom. First we will see the moment of inertia about an axis which is passing from the base of the triangle. So you can get the variation in this diagram, in this derivation methods. Okay, so consider a triangular area of the base B and height h as shown in the figure. Now the centroidal axis passing parallel to the base is at a distance h by 3 from it. As I said, this is the axis which is passing from the centroid. So the centroid of the triangle is at a h by 3 distance. We know this value in the centroid. Okay, so this distance is a h by 3 distance. Okay, now we will consider an elemental strip which is parallel to the x axis at a distance y from the apex A. Now this is the apex A and the distance is y from the apex A. Now the area of this elemental strip is B dash, because the width of this strip is B dash, not B, and that's why we will answer it by the B dash into dy. And why we have written the area of this strip as a rectangular area? Because we have taken the strip thickness very small that the strip looks like a rectangle. Although it is not an rectangle, but for the small distance we can consider it as a rectangle. Okay, so from the similarity of the triangles, we know the similarity rules of the triangles. Okay, so from the similarity of the triangle, which triangles we are considering? This upper triangle and this one, the large triangle. Okay, so we are considering these two triangles. So for this upper triangle, the base is B dash, upon its height is y, and for the large triangle the base is b and its height is h. Our intention is to make the subject b dash. Why we are finding the b dash? In order to calculate the area of the strip. Okay, so we have made a subject of b dash and kept the other things on the another side of the equals. So our b dash answer is b by h up into y. So if you put this value into the equation of the area of the strip and calculate the distance between the strip and the base axis, then your distance will be h minus y, which is very simple and can be seen from the diagram. Our total distance is h and the distance from the apex is y. So if our intention is to find out this much distance only, then it is nothing but the h minus y. Very simple geometry. You need to identify that geometry from the diagram, then apply the formula of moment of inertia. What is this term? This is the area of the elemental strip. And what is this term? This is the distance. So the basic formula of moment of inertia is what? The area into distance square is the basic formula. It looks a little bit complex, but it is not as complex as it seems. It is a very basic formula of the moment of inertia that you have already learned in the previous sessions. Okay, so now what our intention is to find out the moment of inertia for the whole triangular section. And for this section, you need to integrate the whole area by the limits of the 0 to h. Why we have taken this limit? Because our intention is to find the moment of inertia from the base axis. And at the base, our distance are 0, we have taken it as a reference, and at the top our distance is h, so our limit will be 0 to h. So this was the reason behind the limit 0 to h. Now what we will do? We will calculate the moment of inertia by taking out the constants from the integration. So what are the constants? These are the constants b by h. So we have taken them out from the integration, and the rest terms would look like this. Okay, so y is our variable, and that's why we will multiply the y into the each and every members, so that you can get the equation like this. In the first term, we will have to keep the h square as a constant and y as a variable. So integration of the y is a y square by 2. Now y square by 2 into h square, that is the integration of the first term, minus second term is 2h constant and y square integration. So integration of y square is nothing but the y cube by 3 into 2h as a constant term. Now y cube, integration of y cube is nothing but the y raised to 4 by 4. Now if you put the limits in those integrated term, then replace the y with the h and simplify that answer, and then you will get the answer as a IBC, that is bh cube by 12. That is our answer for the moment of inertia of the triangle about an axis passing through the base. Now we will see few more derivation of the same triangle about an axis passing through the centroid. Okay, so let's get started with the thing that is the axis passing through the centroid. Now as we have considered this axis, this will become as a reference axis. So every distance at this axis are datum 0, 0 distance. From this axis to upward distance will be h minus h by 3 or 2 by 3 into h, and the bottom distance are nothing but h by 3 distance. Okay, so we don't have to apply any limits because we are going to apply the parallel axis theorem. So first we have taken the moment of inertia about the x-axis axis is the axis passing through the CG of the triangular section parallel to the base. This is very important. As this is the parallel, we can apply the parallel axis theorem. So the parallel axis theorem is applied over here. We know the formula of the parallel axis theorem, that the axis passing through the centroid will give you the answer of the IG or IXX, and axis which is parallel to the centroidal axis is IBC. So IBC plus IBC equals to IXX plus AH square. That is our formula for the parallel axis theorem. Now what we are going to do is apply the basic formula of IBC that we have already seen in the previous slide and make the subject IXX as this. So IBC formula is BH cube by 12 from the previous slide. H square is nothing but the h by 3 and A is nothing but the BH by 2, because 1 by half base into height, that is the area of the triangle. Now if you simplify those equations, you will get the answer as a BH cube by 36. So this is our answer of the moment of inertia about an axis passing through the centroid of the moment of inertia, that is BH cube by 36. Now we will see another derivation, that is the derivation of moment of inertia about an DE line which is passing through the apex is parallel to the x-axis axis. Again, this line is parallel to the x-axis axis, and that's why we can directly apply the parallel axis theorem over here. So our intention is to find out the moment of inertia about this axis, and that's why we need distance between the two parallel axes, and that distance is nothing but the h, that is 2h by 3. Now if you apply the formula of the parallel axis theorem, that is IDE equals to IX plus AH square, then we have the value of the IX, that is nothing but the BH cube by 36 from the previous slide. Okay, we have the area of the triangle, that is 1 by 2 B into H. We have the H value that we have already seen over here. So if you put all these values in this equation and simplify the equation by taking the LCM and simplify that equation, that you will get the answer as a bh cube by 4. So this is the moment of inertia about an axis which is passing from the apex of the triangle, and apex of the triangle is A, and the axis passing from this A is nothing but the DE. And if you are in your examples, if you know this formula, then you can directly apply this formula in order to reduce the length of your example. So you need to remember those formula. No need to remember the derivation in your examples. The derivation can be asked in your theoretical part, but in examples the only formula is important, and if you know the formula, you can directly apply this formula in the appropriate form and put the values which are provided and find out the value which is unknown. So your examples will be easier, and if you know and remember those formula only. So this was our lecture in which we have seen the basic derivations of the different basic parts like a rectangle and a triangle, in which you can divide your complex figure in order to find out the moment of inertia of that particular complex figure. So if you are you need to remember this derivation, because this can be asked in your examination in the theoretical part into the 5 or 7 marks, and based on the marks you need to explain those derivation so that you can get the full marks. And after the derivation portion, those are important for your example point of view also. So you need to remember the last formula which is available from the derivation, and if you remember that formula, you will be easily calculating your examples in the next section. Till then, thank you.